Okay, so it's all right. Okay, good. Thank you so much, Syed. We'll keep moving on. You don't have to stay if you. Yeah, that's all right. Okay, so good. So we'll continue from where we were at, and we were talking about capacitances, and capacitance was defined, and the defining equation was Q equal to CV, which everybody remembers, which is good because it's a good thing to remember because everything comes from there. That's a defining equation, so there's no need to say where does this come from. It's a defining equation. And people have defined it this way. It's up to us to make definitions. And humans have defined it this way because they discovered that there is a relationship very close to linear, a relationship between amount of charge and the voltage across a pair of conductors that are separated by an insulator. So once you have that definition, then you can do various things. And you can look at the process of charging a capacitor, for example. And you would charge a capacitor with a current. And if that current was constant, the capacitor would charge at a constant rate. That rate would be the rate at which the charge is going up. And so that means dq dt equal to C. C is a constant. You could say that is d by dt C times V, but C being a constant, you can take it out. So you can say then dq dt equal to C dV dt. But dq dt, the rate at which charge is going into the capacitor, is just current. So that gives you I equal to C dV dt, which is a very important equation. Of course, and it is what I have called, I use a word before, the word that I used before was relationship. And that's a relationship. And we like that relationship better than this one as electrical engineers, because as electrical engineers, we are more likely to deal with current and voltage rather than charge and voltage. So that relationship is a better one. And of course, it is between current and voltage. And we like relationships between current and voltage. Just like for a resistance, it's a nice proportional relationship between current and voltage. So for resistance, it's a proportional relationship. For capacitance, it's not a proportional relationship. Of course, it is proportional there when you relate Q to V, but it's not proportional when you look at I and V. It's a differential relationship. So we're starting to see differential equations. So for a resistance, it's not a differential equation. It's just a normal equation, V equal to IR, and people are very comfortable with that. And people start getting uncomfortable when you say, oh, now it's a differential relationship. But these differential relationships can become simpler for sinusoidal steady state. And that's what we'll talk about, because in this course, protection, most of the time we are dealing with sinusoidal, most of the time, not all the time, most of the time we are dealing with sinusoidal responses. Now, if you look at this sinusoidally, then you would have this there. You apply your voltage across the capacitor, C, and this is I. I put them lowercase because I'm going to draw the waveforms. We use lowercase when we are looking at instantaneous values, and we use uppercase when we are looking at RMS values. So if you look at this, and you say, okay, how does this look like sinusoidally? These are sinusoidal quantities. You would have current, and if the current is a sine wave, so I'll draw the current there. If the current is a sine wave, then most of us know that if the current is a sine wave, the voltage will be a cosine wave, and I'll talk about this very soon. So that's the voltage there. So voltage is a cosine wave. So I, the current is some peak value, sine omega t, say, and the voltage is some peak value. The voltage V is some peak value times cos omega t. So the current then, if it is a sine wave, the voltage is a cosine wave. And you can see that the voltage leads the current by 90, sorry, the current, oh, I've got this the other way around, did I? I have to rewind, please. I have to go too quickly. So, did I say the current? Let's make the current a. Let's make the current a cosine wave. So it leads. So the current. So I'm doing this again. Current is I cos omega t, and the voltage is a sine wave. Yeah, that's good. So the voltage is a sine wave. That's voltage there. That's voltage is a sine wave. Okay. You will see that this matches that one. And I'll do this match very soon. So let's say you had a current. That's the peak of the current there. So the current is a cosine, as I said before. So the current is a cosine. And the voltage is a sine. And you can see the peak of the voltage appears 90 degrees later compared to the peak of the current. Therefore, the positive peak. So positive peak of voltage, 90 degrees later. So that's saying voltage for a capacitor, voltage for capacitor lags current, lags capacitor current by 90 degrees. So let me rewrite it down. I'll say for capacitor, voltage lags current by 90 degrees. And you can see that there. For capacitor, voltage lags current by 90 degrees. That is obvious if you think about it. If you have a capacitor with voltage across it, then it means sometime in the past, current must have gone into it. So you don't have to read 25 books and worry about it. It is obvious that for a capacitor, current has to come first before it can be charged with voltage. So therefore, current leads. And for sinusoidal situation, it leads by 90. And you can see that this matches your first principles, because if the voltage is a sine, which it is here, and if you differentiate a sine, you get a cosine. So here it says differentiate voltage, you will get current. And you can see if you differentiate the sine, which is the voltage, you will get cos. And cos leads sine. Cos leads sine because cos, peak of cos happens first. Cosine, the peak for cosine is at 0 degrees, whereas the peak for sine is 90 degrees. I hope you have sketched enough sine curves and cosine curves in your life so that this is natural to you. If you are I'm hoping that some of you will be power engineers. So if you're a power engineer and you have never sketched a sine curve or a cosine curve, I think you should not be a power engineer. You should be something else. So a power engineer naturally draws those sine and cosine curves and know that the cosine curve peaks at 0 degrees, the sine curve peaks at 90. In trigonometry, you would know that as well. Okay, anyway, so that's the situation. And you can see, of course, that this matches that one, as I say, because the differential of sine is cos. From that too, you can see those people who are worried about this calculus just see that this is natural. The gradient, what we are saying here is that the gradient of the voltage is equal to the current, or at least proportional. So you can see the gradient here is maximum and positive. As you go up, the gradient is dropping. Of course, you can see the gradient. The red one is the gradient, so you can see it dropping. And you can see that the gradient is 0 here, so that gives you a 0 current. And in practice, that makes sense. I am over here. Am I charging at this point here? Am I charging or discharging the capacitor at this point? Okay, before this point, am I charging or discharging the capacitor? Before this point, from 0 to 90, am I charging the capacitor? It's charging. I know I am charging it because the current is positive. So the current is going into it. So I'm charging it. So therefore, its voltage goes up. On that side, here, what am I doing? Am I charging or discharging? Discharging because the current is negative. So I'm discharging it, so no wonder the voltage is coming down. At this point, what am I doing? Charging or discharging?
Just the voltage across it.
No, I asked the question. The answer is yes or no. This is a court case. This is court. Answer only by yes or no. So at this point, am I charging or discharging? At this point, this one here. What's the current there? 0. The current is 0. So am I charging or discharging? The current is 0. Am I charging or discharging? None. That's right. I'm neither charging nor discharging. If I'm neither charging nor discharging, what should the capacitor voltage be doing? What would it be doing? If I'm neither charging nor discharging, which is happening there, the current is 0, therefore I'm not charging and I'm not discharging. So what should happen to the capacitor voltage?
Just constant.
Just constant. And you can see this happening there. It's constant, right? So this graph is telling you a lot of stories and you're missing them all. And this is what's not good. This graph you should listen to it. And it's telling you, here, current is positive. I'm putting current into the capacitor. So the voltage must be going up. So you can see the voltage going up. The graph is talking to you. It's telling you, oh, here, current is negative. So I'm taking current out of the capacitor. So its voltage is coming down because less charge. That equation tells you less charge, less voltage. So if I'm sucking charge out of the capacitor, its voltage is coming down. And I'm sucking charge out because the current is negative. And then here, specifically here at this point, the current is 0. That is, I'm neither charging nor discharging. So the voltage is staying flat, the same. Right? So if you don't see that, then you don't understand capacitance. And if you don't understand capacitance, you don't understand electrical engineering. And if you don't understand electrical engineering, you cannot be an electrical engineer. Right? So make sure you understand it. Make sure you understand the stories that this graph is saying. Okay, continue. We can, of course, represent that by phasor diagram. I'm not going through the full theory of phasor diagram. You're supposed to have done this. You can draw that here, and you can show that if you were to use the current, you were to show the current there as I for the current, then the voltage comes later, so it lags there. So for capacitor, that's your phasor diagram. Some people say that, oh, this is rotating. You can think of it as rotating. And if it's rotating, then you will see the current first. The current arrow will face you first. This is an I watching this. So you would see I, and then you will see V 90 degrees later. So you can represent all this thing starting from here, which is what people have observed, that Q equal to CV. They have defined C. They have observed that Q is proportional to V. It's proportional, so it was a proportionality relationship. They made it an equality relationship by inventing a capacitance, which is a constant of proportionality. From there, you get to here, you get to current. And from current, if you plug a voltage that is a sinusoid, you will get a current that will be a cosinusoid, giving you that 90-degree phase shift. So the full story of capacitance is actually just here. Here is everything there is to know about capacitance, about a linear capacitance, because we have assumed that it's a constant. Okay, so any questions about capacitance before we move on to inductance? So we have now covered 4 of the 5 elements that we're going to use. I remind you, they are current source, voltage source, resistance, capacitance, and the last one is inductance. So let's talk about inductance. I'm confusing a bit with my other class because we talk about that there as well, but I did not give them the full theory behind inductance. But I'll give you the full theory, and then we'll share lectures between you and them. So they will get your lectures on the 5 elements of the circuit, and you will get their lectures on transformers. And then both classes would be up to date. So, inductance. I did capacitance first because it's a little bit easier to understand. People realize that matter is made up of charges. All matter, every bit of matter is made up of charges, positive and negative charges. We can separate those and keep them separate by putting an insulator in between the positive and negative charge. And when we do that and we keep them separate, we get capacitance. And in keeping them separate, we are storing a charge, some people say, or we are storing energy. The same thing, really. But in this course, we will look at energy at some point. And when we get there, I'll describe it a little bit more. But remember, the capacitance also stores energy. Okay, let's go to inductance now. What is inductance? Just like we asked a question, what is capacitance? And I remember you gave the answer. The capacitance is the ability to store charge. And you can store charge, as we say, by putting an insulation in between some positive charge and some negative charge. And if you do that, you've stored charge. So we might ask the same question. So capacitance is the ability to store charge. Anything that has capacitance, what would have capacitance would be a group of bodies. One body by itself cannot have capacitance, but a body close to another body, conducting body, would have capacitance. Like my body and the Earth, we have capacitance. Me together with Earth, we have capacitance. I wear insulating shoes. I am a conductor. The Earth is a conductor. So I and the Earth form a capacitance, obeying those equations that we have seen before. Now we ask the same question. What is inductance? It's a bit harder to answer this one, but just remember, we were able to answer what a capacitance is by admitting that charges exist. If you don't admit that charges exist, then you can't define capacitance. Then you might as well again go home and watch TV. So as an electrical engineer, you have to admit that charges exist. Someone told you that charges exist, and you say, okay, charges exist. And from there on, you are able to define capacitance. Now, with inductance, how do we define it? What is inductance?
Ability to store magnetic energy?
Yeah, I think that's not a bad definition. Ability to store magnetic energy, or ability to create a magnetic field. And we know that a magnetic field exists. People, I think even before Faraday, knew that magnetic field existed. What was the first manifestation of magnetic fields? So how did people first had an idea that magnetic field could exist?
I think the Chinese found lodestone, didn't they?
Yeah, that's right. So the Greeks and the Chinese, I don't know who found it first, and I don't worry too much about that, whether it was the Greeks or the Chinese. Could have been the Chinese, I think. But the Greek people definitely also were very much aware of it, and that was natural stones that were magnetized by the Earth's magnetic field, and they realized that there must be a force there that is related to those magnetized stones. And so that was the first realization that there is a field. And people say a field is an influence. I should have said before that don't be afraid of the word field. You can have all sorts of fields, and we have, if you want it mathematically, we have what we call a scalar field. And I see fields as sets of numbers in space. They're scalar fields and they're vector fields. So an example of a scalar field, can you give me an example of a scalar field? So again, field is a set of numbers in space, that's all. A set of numbers in space. So an example of a scalar field. Scalar means just a number. It doesn't have direction, it's just a number. An example would be a field of temperatures. Now, picture in your mind, field of temperature in this room. So where would be the high regions, high temperature regions in this room? What's the temperature here? Approximately. What's the temperature here? 20. Okay, 20. So you can see number 20 in this room. Lots of number 20s in this room. And can you see numbers other than 20 in this room? Yeah, an example?
25 close to the left.
Yeah, maybe 25 close to the left.
Or 15 close to the AC.
Sorry?
Or 15 close to the AC
Oh, yeah, oh, 15 close to the air conditioning. Yes. So we can see numbers, can you? 20, 15, 25, 15 coming out of the air conditioning, 20 here. So you can see in space, you can see a field of numbers. Any other numbers? Any other temperature in that temperature field? Anything else? Any other temperatures in this room? Yeah. That's right. We are not dead. We are all alive here. So what temperature in our body? 37. Is it 37? 36 point something? 36 point something. So you can see a field of numbers in space. And in this case, it's a temperature field, a field of temperatures. So that's a field. On TV, when you watch TV every day, you see a field of pressures. They might show you. They say, oh, this is the map of Australia. They draw some contours. You know what contours are? You don't know what contours are? Contours? Contours? Okay. So the plot points, you can do that for temperature. If you draw the temperature around me, it will start with high values because I'm not dead. So it will be like 30 something, 35, 36, very, very close to me. And then as you go away from me, the temperature would drop. So you can see fields of temperature. That could be me there, and then you are there, right? So that's contours. So on TV, when you watch, they show you contours of pressures. Have you seen this? And the cyclone could be somewhere in that set of contours. Isobars, they are called. Yes. They've got special names. Isobars. Actually, these have got special names as well. The one for constant temperature, what's the name? Isotherms. So you have isobars and isotherms. So these are contours. We also do contours when we look at fields. And we go lines of constant potential. I don't know whether they got a name for them, but they are also contours. You can see contours around conductors. These will be contours of constant voltage around the conductors. Anyway, so you can have a field of temperatures, as I say. So a magnetic field, it so happens, is also a field. But in order to understand that one, you need to, first of all, you need to understand that the field is a set of numbers. So you have a temperature field or a pressure field. Now, a pressure field, is a pressure field a vector field or a scalar field? It's still a scalar field. You have regions of high pressure and regions of low pressure. But there are vector fields, as I say. Can you name an example of a vector field?
Wind.
Yeah, wind speed. Wind speed. So wind speed is a vector field because at every point in space you will have air moving at different speed and in different direction. So if I were to show you the wind speed, that is the field of wind speeds, it will be like this. I believe they do show that on TV sometimes, eh? So they might show this. So they show you a set of arrows now these days on TV. So that would be a vector field. So the best way to represent a vector field would be by arrows, where the length of the arrow might represent the magnitude of the field, and the direction of the arrow representing the direction of the field. Now, just like you have a field of pressures, a field of temperatures, you can have a magnetic field. And that magnetic field is characterized by a set of numbers in space And those numbers would represent the influence of the magnetic field. So if I show you a magnetic field around a magnet, which a lot of people do, so if I magnet north, south, and I represent the field like this, then that's a vector field. That's a vector field because I am representing the field by both, in this case, just by directions, but you can also see magnitude there. Magnitude is the concentration of those lines. So where those lines are, when you got lots of them, it means it's a strong field. Where the lines separate, like here, it means the field is weaker here. And as I say, it is a field of numbers. The numbers would be usually the flux density. So you would see the flux density as a number. So you will have a high number here in space, representing the high flux density there. If you buy a magnet, which I've played with a few months ago, a neodymium magnet, the flux density around here, close to it, would be 0.5 Tesla in air. And then as you go away, it drops. So over here, it could be milliteslas if you are like a few centimeters away from the pole. A few Teslas in that direction. So you can see that this representation of the field is just a set of numbers, but it's a vector field, so those numbers, which would be the flux densities, would be, those numbers would have a magnitude and a direction. So it's a vector field. So electric fields and magnetic fields, they are vector fields. Field of temperatures, they are scalar fields. So again, don't let the word field get you confused. If you are, I don't think you should be an engineer. Just remember that the field is just a set of numbers in space, in three-dimensional space. It's a set of numbers. Now, those numbers can be high or low. So if in space somewhere the magnetic field is low, then the flux density there would be low. But for our work, magnetic or electric field, we are dealing with vector fields, which means that those numbers have both magnitude and direction. So therefore, somebody could say, oh, it's a pair of numbers in space, and that would be fine, because you could describe the field at a point in space by both a number giving the magnitude and another number giving the direction. Now, when you look at a magnetic field, like this is, you're talking about flux density, which is a quantity, which I think most of us would relate to flux density better than we would relate to flux. At least I do. Flux density, I am happy with it. I am happy with it because it goes right back to what we know about the influence of magnetic fields. If someone were to tell you, I don't believe that magnetic fields exist, you could tell them, well, I can't show you the magnetic field, but I can show you its effect. What would be one effect you would show to people? If you're an electrical engineer, so you're the one who can do it best. Nobody can do it better than us. So how would you show to people that magnetic fields exist? Because, of course, the magnetic field has an influence. So what would you will show the people the effect of the magnetic field. So what effect would you show to people to get them to believe that magnetic fields exist?
North poles repel, south poles
Yeah,
repel,
yeah,
north
you-
and south attract.
Yeah, you would do that. You would say, look, got two magnets here. Look, see, they separate. If I do that to two pieces of wood, nothing happens. So surely there must be something that exists there, and let's call it magnetic field. So that's all it is. However, for our business, which we are now doing, the example of the two magnets is fine, but not the best for us. So there must be something else we could do. Numbers? Yeah, but that's not an answer. If you just say, you have to say something you would do somebody's coming to you and saying, prove to me that magnetic fields exist. You can't just say numbers. You have to do something. So what would you do? To prove that magnetic fields exist. I'll give you a bit of a clue, because it leads to what I'm going to say.
As you said, the temperature, given temperature varies from one place to other. For example, in this room.
Yeah, but that doesn't prove that magnetic fields exist. Your example was good, Gordon, but I'll go one more step. It so happens that, and that's very, very important, otherwise you won't get forward, you won't go forward. Very, very important. Yes, two magnets would repel, etc., and that does tell us that there's something there, and we've just called it magnetic field. But there's another discovery, of course, that people made. You could have a permanent magnet, but what's the other magnet you can have? What's the other magnet you can have, apart from a permanent magnet? What's another magnet that's not a permanent magnet? What's another magnet that is not a permanent magnet? Is that a magnet? That's a coil. Is it a magnet? It is a magnet. I hope this shows on the. Have you heard this word before? Yeah. Is this a magnet? Who was your physics teacher? Did you ever have a physics teacher? This is a magnet. It's an electromagnet. It's not a permanent magnet. So my question was, is there a magnet apart from permanent magnet? And I thought that was good enough clue for you to realize that there is such a thing as an electromagnet. A magnet has flux around it. The flux is described by flux lines. And when you look at the pattern of flux lines, you recognize regions of high flux density and regions of low flux density. In order for me to give you a good indication of what flux density is, I need to go to electromagnets rather than permanent magnets. Now, with the electromagnets, you get exactly the same flux pattern. If you want to do this properly, you go and draw it. So this will be an iron core, and you would put wires around it like that. I don't know if you've done this before. I drew this a bit long, so I'm drawing this because I see you've missed quite a lot of things, and it does worry me that. So you would put current in. Have you seen this before? The cross stands for current going this way, and the dot for current coming that way. And this is a two-dimensional representation of coil going around. Is that all right? Yeah. So you go like this. and that now is a magnet. Of course, it's an electromagnet. I assume I've drawn the same numbers there, same number of. Each pair of those is a turn, right? Okay, and that gives you the same set of flux that we had before. So we had flux lines going like this. So this is a magnet as well. Right? So that's an electromagnet. So people discovered that. They found, not too long ago, in terms of human history, it's not too long ago. It's only about 400 or 500 years ago. People discovered that an electrical current creates a magnetic field. And you can make the electrical current behave the same way as a magnet. So associated with that electrical current is flux. And that's the beginning of it for us. Associated with an electric current is flux. Now, how do we, as I said to you, I find flux density something easier to picture and measure than flux. And the relationship that allows you to understand this is this one. So I'll rub this off. Now we know that associated with an electric current, we have flux. We can get flux from a permanent magnet, but we can also get flux with an electric current. We haven't quite said yet what we mean by quantity of flux. So I would like you to understand what quantity of flux means, because to understand what inductance is, you have to understand what quantity of flux means. So I don't want people to go around and say inductance, 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 and not knowing what it is. You have to know what it is. So that's why I'm taking the time to explain what inductance is. Inductance definitely is associated with flux, flux created by a current. But what is flux? And in particular, what is quantity of flux? Indeed, when we talk about flux, it's a very loose term because it's quite legitimate to talk about flux. But you can never go mathematical if you don't go quantity of flux. Quantity of flux makes sense. It's just like saying water. Water is a word that makes sense. But you can't do calculations when you just say water. You can only do calculations when you say quantity of water, whatever that is. Quantity of water flowing in a pipe per second. Quantity of water that fell on the roof. You have to put the word quantity in front of it. So you can talk about flux, that's fine, but your talk would be fairly general. When you get serious, you have to talk about quantity of flux. So what is quantity of flux? Now you can understand what quantity of flux is if you start from flux density. Now, you can easily see this will be a region of high flux density. But what does that mean? How would you measure it? I relate it back to an influence. How do you know the flux density is high there? I relate it, as I say, I'll draw a permanent magnet there again and ask the question. So permanent magnet again, because all of us know what that is. Again, you have flux there. Again, you have flux there. And just from our own experience with magnet, we know that the flux density is high here and it will be low over there. Now, if I now say, how would you prove to someone that the flux density is high over here? And you could quite easily say, oh, well, as I take my magnet, another magnet, and as I go towards there, I can feel the bigger force, so I would say the flux density must be high here. That is fine. That is okay. But the one that I prefer, because I can actually think of experiments that I can do and measure things is F equal to BIL. I like that one. And it so happens that you use that in relays, in electromechanical relays that we don't probably make anymore, but we use that. Anyway, so if I wanted to, and that's flux density, so that's flux density, magnetic flux density if you want to be precise. So because there is such a thing as electric flux density as well, so it's really magnetic flux density. So if I wanted to actually measure, so we're putting numbers in now, if I wanted to measure the flux density here, I would just take a wire of length, an appropriate length. So if it was a small magnet, I'll use a smaller piece of wire, and put 1 amp through it and measure the force. Hopefully you've done a bit of physics and you know that if you had a current here, say going into the board, so you had a conductor with a current going into the board at this point, there will be a force on it. In what direction would that force be? So which one is field? I don't teach first years anymore, so I can forget. So that's field, second finger current, so that's in there.
And force.
Yeah, so that's right, is it? That's right. That was an excuse, by the way, me not teaching first years anymore. It's good to remember this. One of the lecturers about 30 years ago said, generator, that's for your right hand, and then the other one is your left hand for a motor. So motors works this way. So field there, this one, field, magnetic field is this one. Current is going into the board, that's that one, and that gives you the force. So there's a force going that way. So I like that because it allows me at least to fantasize about a method of measuring the flux density. So if I wanted to measure flux density, I'll have a piece of conductor of length L. I put 1 amp in it, and I measure the force, because I could have a spring balance. If I did that all very well, I have a spring balance on this side here. Switch on the current, it will pull, and my spring balance would tell me what the force is, and I'll be able to get the flux density. So I have a very good concept of what flux density is. I can measure it. If you pay me enough money, I'll measure it for your magnet. I charge, of course I work for the university, they would charge you about $400 an hour. So I could do one for you and measure the flux density. So it's something real. That force is real, we can feel it. It's bigger. If the magnet is stronger, it's going to be bigger. We can measure it here, we can measure it there. The force will be in different direction depending on where we are. So this is real. The flux density is real. We can't see the flux lines, but certainly we can feel the force. And we can, from that, determine that flux density. So anyone here don't believe the flux density? It's proven. So it's there. Now, once you understand flux density, you can go from flux density to quantity of flux very easily. So what is quantity of flux? How would you define it? Let's say now you understand what flux density is. What is quantity of flux? So note, I'm not saying flux anymore. I'm being very careful. I'm saying quantity of flux. People most of the time drop the term quantity. And maybe that's behind a lot of people getting confused as well. Because if I talk about water, and I have to say amount of water or quantity of water, and I drop the amount or quantity, it can get confusing. People say, how much water? How much flux? What is the quantity of flux? What is the amount of flux? So behind flux, many times we just say flux, but we really mean quantity of flux. So what do we mean by quantity of flux? And how do we go from flux density to flux? How do we go from flux density to amount of flux? Yeah?
Flux in Webers, flux density in Webers per square metre or Teslas?
Yeah, that's the units. Yeah, that's the units. But I was more after how would you calculate the amount of flux from flux density. What do we mean by density anyway? Density in mass terms, how do we go from density to mass? If I say, my density or my average density is 1 gram per centimeter cube, how do I go from that piece of information, which is my density, to my mass? Whenever you have density, which is density is more or less a point variable. This means it's a variable at a particular point in space. How do you go from there to a quantity variable? So from if my density was 1 gram per centimeter cube, what would be my mass? What more information do you need? Yeah, that's right. So you need volume. So to go from the quantity of mass in my body, you take the density, you multiply by the volume. Now, how do you go from flux density to quantity of flux? Multiply by the area. Because flux density is amount of flux going through a unit area. That's what flux density is. So unless you know that, you're not going anywhere. You will be talking and using words, you have no idea what they mean. And that's what we don't want. We get paid at the university to make sure that when you use those words, like flux density and flux and voltage and current, you know exactly what you mean. So if you're going to use the word flux, please make sure that you understand what you're saying is really, most of the time, what you will be saying is amount of flux. It's a certain amount. And that amount can be calculated from flux density. Flux density itself is the intensity of magnetic influence at a particular point. So if at a particular point you have high flux density, then it means that there will be a magnetic influence that's very high at that point. You can go from flux density to amount of flux by multiplying the flux density by the area, because flux goes through an area. The key word is through. Flux goes through an area, and the amount of flux going through that area is the flux density times that area. But be very careful, this multiplication is not a normal multiplication. It's not a scalar multiplication. Why isn't it a scalar multiplication? I told you when I did this, I told you there are two types of fields. What were the two types of fields? Scalar field and vector field. Now, when I do the multiplication, flux density times area, it's not going to be a scalar multiplication. What sort of multiplication would it be? Not a cross product, a dot product. It's going to be a dot product. Have you heard of a dot product before? Yeah, right? So, so when you go from flux density to amount of flux, you will be using a dot product. Please go and read about the dot product so you know exactly what it means. That's where we are using it. Thank you very much. Thank you for your participation. I really enjoy that. I'll see you next time.